Hi, welcome to series of webinars on optical network technologies and protocols. This is your friend Brahmanand GS in the journey of learning. Today's topic of discussion is optical transmission impairments and compensation. In the last session, we discussed about the parts of transmission link. We discussed that it has a transmitter, it has got a receiver, and the optical fiber is used as a transmission media between transmitter and receiver for transmission of data as light. But in practical, as we know, optical fiber is made of silica, the glass, which is not completely ideal. It means that it can have impurities. So when there are impurities, then the refractive index of this core varies at different points, which gives rise to scattering. So the signal will go away from core and enter the cladding. And also, when an optical signal traverses an optical fiber, the impurities which are present in the optical fiber might absorb the signal light, making the signal strength to diminish. So scattering and absorption causes attenuation in optical fiber. So based on the experiments by the scientist, it's proved and found that attenuation in optical fiber is not constant across all the wavelengths. So if you write a graph between wavelength against optical loss, the optical loss is varying at different wavelengths, and it is quite less at certain different windows based on the year of research. A couple of decades back, the first window, which was found that around 900 nanometer, the loss was less, and after further research, we found the second window, wherein we found that at 1310 nanometer, the attenuation of the optical fiber was less. Similarly, the third window is at 1550 nanometer, where we found that the attenuation is less. And the fourth window is approximately at 1625 nanometer. So these wavelength ranges are put into different bands called S band, C band, L band, based on a research outcome and based on the wavelength. So the C band ranges from 1530 to 1565, L band ranges from 1565 to 1625, and this is the range which is widely being used for optical fiber communication as on today. Attenuation is calculated as follows, and output power is equal to input power minus attenuation of the fiber per kilometer into the length of the fiber. So this particular output power calculation is very important when we design our optical network. The second important factor or the physical characteristics of the optical fiber is dispersion. Dispersion is the spreading of light pulses as they travel down the optical fiber. There are two types of dispersion. One is chromatic dispersion, the second is polarization mode dispersion. First is chromatic dispersion. So different wavelengths travel in optical fiber. See, it's something like a rainbow. So rainbow has got different colors. If you pass a white light through prism, you will get 7 different colors. And we can notice that their inclination varies. It means that their speed varies. So when a light traverses through optical fiber, it means that there are different wavelengths signals traveling through optical fiber. So we know that group velocity is equal to c by n, where c is the speed of light and n is the refractive index of the fiber. So the refractive index of the fiber can also vary because of the impurities, and similarly the group velocity can also vary because they are it also depends on the wavelength. Because refractive index depends on the wavelength, the group velocity will also vary. So because these wavelengths travel at different speeds, they reach the destination at different timing, different interval in time. So which gives rise to prolonged pulse. So this makes it difficult for one to differentiate between the ones and ones and zeros. So this is what is called as a chromatic dispersion. Chromatic dispersion increases based on the wavelength. The wavelength increases, the chromatic dispersion also increases. Chromatic dispersion is calculated as picoseconds per nanometer per kilometer. Chromatic dispersion also varies based on the data rate. Chromatic dispersion is calculated as pulse widening, which is equal to chromatic dispersion in picoseconds per nanometer per kilometer, the length of the fiber, and the spectral width of the input signal. Polarization mode dispersion. So different polarization states of the light travel at different speeds. Light would have different polarization states, and they have different energy. So the pulses travel based on their energy, which is the polarization state of it. So because the pulses can spread across, they can overlap with other pulses, and eventually they can change their own shape. So this is what is called as polarization mode dispersion. And polarization mode dispersion increases drastically when the data rate increases. So when we plan our optical transmission network, we need to see what is the data rate against what is the accumulated polarization mode dispersion before it gets compensated. So this is is um, basically measured in terms of differential group delay between polarization states. Basically, polarization dispersion is caused because of the manufacturing process, like the core dia might vary, the stress on core, and other mechanical stress, bending of the optical fiber, twisting, the vibration, heating, cooling. These kind of mechanical stresses can also give rise to polarization mode dispersion. Polarization mode dispersion coefficients are in units of picoseconds per square kilometer. We can use some polarization mode dispersion compensation fibers, or we have to design our link such that optical signal to noise ratio is higher whenever there is polarization mode dispersion. So we have to plan for additional OSNR for compensating PMD. Otherwise, we can reduce length, or we can have optical to electrical back to optical conversion, so that once the signal gets regenerated in the electrical domain, it will get reshaped as well, so that chromatic dispersion can be nullified and it can be retransmitted again, so using regenerators. Or we have to install new fiber with better PMD coefficient. Apart from this, attenuation and general attenuation due to scattering and absorption, and dispersion due to chromatic and PMD, there are certain nonlinear effects which are very important, which gives rise to losses when optical power is very high. Some of these nonlinear effects are stimulus-Brillouin scattering, Raman scattering, four-way mixing, self-phase modulation, cross modulation. So this nonlinear effects would be discussed in a separate session. But just to give a heads up, these nonlinear effects becomes very vital for our network design, because when these are accumulated, they give rise to huge losses over distance. So how can we improve these impairments that we discussed so far? The best way to improve these impairments is to plan and use very optimized fibers. There are basically three classes of a single mode fiber. Non-dispersion shifted fibers, which is based on G652, which is typically a standard single mode fiber, and whose dispersion is 0 at exactly 1310 nanometer. So if for any communication, if you want to use 1310 nanometer, if you use 16 G652 fiber, then absolutely the dispersion is 0 at this particular wavelength. So this fiber is manufactured such that this dispersion is 0 at this particular wavelength. Similarly, dispersion shifted fiber is G653, where dispersion is 0 at 1550, whose dispersion is shifted to some other wavelength. So non-zero dispersion shifted fiber is 0655, dispersion is 0 at certain wavelengths, whereas we can use in combination as well as we can use G655 independently, because the dispersion 0 point is at a particular wavelength of our need, and it can exactly be used at that particular wavelength. So this is a high level view which differentiates between non-dispersion shifted fiber and dispersion shifted fiber against wavelength versus dispersion. So we saw in one of the slides that non-dispersion shifted fibers, dispersion increases drastically over wavelength. But if we observe dispersion shifted fiber and non-dispersion shifted fiber, the attenuation or dispersion, the dispersion is almost zero, nearer 1550 nanometer. So we can use these bands for our transmission. We'll discuss about different types of wavelength division multiplexing in a separate session, but to give reference to these fibers and their usage in different bands, we can say that G6552 can be used both in C band, L band, and G653 cables can be used in L band and for TDM communication, and G655 can be used at C band and for TDM communication. So when I say C band, I'll have to use either G655 or G652. Similarly, if it is an L band, I'll have to use 653 or G652. And for TDM communication, using for say like optical networks like SDH SONET transmission, it is better to use G653 optical cable. We can also improve the transmission. We can optimize the transmission by encoding such that we encounter less bit errors. There are different ways of encoding techniques: non-return to zero, optical duobinary, return to zero, carrier suppressed, return to zero. And also we can improve the transmission by using proper optical amplifiers and regenerator at the right places based on the network design. So regenerator, it re-amplifies the attenuated signal, it reshapes and reduces the noises and the jitter in the signal, it retimes my pulses, and then it gives a proper pulse to the destination. So re-amplification, reshaping and retiming can be done by a regenerator. So planning of regenerator in my transmission link is very vital before the signal gets completely diminished beyond limits wherein I cannot able to recognize the signal itself. So optical amplifiers should be used. Different optical amplifiers we will discuss in a separate session. Should be used such that they are planned for proper optical output power, proper gain of the signal, and for reduction of noise level. I mean, these parameters should be well considered when we design our optical amplifiers. Compensation fibers, DCFs, as part of my link to compensate the dispersion already caused in my network. I can use non-zero dispersion shifted fibers. So non-zero dispersion shifted fiber will not move away from the wavelength of operation. Instead, it will only compensate the already dispersed signal to give rise to the original signal. So dispersion compensated fibers are widely used in the transmission links to compensate the already caused dispersion. One more thing, dispersion compensation fibers can also be used at the beginning of the link, at the end of the link, and at the middle of the link. It can compensate already dispersed signal. What I mean to say is, it can compensate the dispersion already caused, or it can also compensate the dispersion which will going to be caused in the link. So this plays a vital role in my transmission planning. This is about the transmission impairments and compensation in optical transmission link. These concepts will help us in planning an optical transmission network. Thanks for watching. If you like my videos, please click on the like, and if you would like to be part of next series of discussions, please subscribe to my channel. Thanks for watching.